Hey, AK again. Welcome back. This is the third video in the series 1 Hour Matlab. In this video, we will take a look at Matlab functions. Whenever you're doing certain tasks repeatedly in your code, it is time to wrap those lines of script inside a function. As usual, we will start with a practical example to illustrate the concept and set up the problem before we jump into Matlab coding. Imagine you are a scientist working in the modeling and analysis section of a private space launch company. Your department is actually given a data file that contains launch data from an actual rocket flight. By the way, a disclaimer, this is a fictitious scenario. I haven't used any data, classified or otherwise, from any actual rocket. This is purely fictitious data for illustration purposes. The data file this time is not a text. Let's go to Matlab. So the data file that we are talking about is not a text, or in other words, ASCII file format. Rocket launch data.mat. This is a Matlab binary file format. Okay. Humans can read this file format, but computers can, and this format is very efficient compared to the ASCII file format, especially so for large data sets. Okay. And this rocket launch data.mat, it has 5 data elements. The first one is a float, earth radius in meters, and the second one is a vector of floats, time vector, and the third one is the rocket height. It's again it's a vector of floats, and this one is the rocket airspeed, again a vector of floats, and the last data is a launch angle, which is again a vector of floats. Okay, so this is the vertical line, and this line is actually approximately the way the rocket nose is pointing. So the launch angle, again, roughly speaking, not very precise in aerodynamic definition, is the launch angle is the angle between the vertical line and the way the nose is actually pointing. Okay, so that's the launch angle. And the first thing we want to do is to understand how these variables of interest are actually evolving over time. We just want to plot the data from this file and understand how the variables are actually behaving. Okay, so we open this 1 hour Matlab 3 rocket launch analysis, which is the main script for this this video. And the first thing we want to do is actually load rocket launch data.mat. All right. So put a breakpoint here, run. I'm going to go a little bit faster because this is all known stuff. And step. Okay, this is all plotting stuff to make the plot look pretty. So don't worry too much about it. Just concentrate on once we actually execute this load command. Observe here in the workspace, and we have all the data variables loaded into the workspace with the proper names. We have in alphabetical order, right? So we have the earth radius, which is a float, and all of the other variables are just a vector of floats, just as I described. Okay, so I'm just going to place a breakpoint here and just say continue. We run up to this point, and this is actually known stuff. In a subplot, we are actually plotting the rocket height and the rocket airspeed and the rocket launch angle, which we talked about before. So I'm actually going to set the breakpoint here and actually say continue. And this is how the rocket launch variables actually behave. Time versus rocket height, time versus rocket airspeed, and time versus launch angle. Now it starts pretty close to 90 degrees, which is approximately vertical. Then the launch angle actually gradually comes down. So this is all well and good. Okay, so what we want to do in this video lesson is understand a little bit more about how MATLAB functions work. Okay, now that we have an idea of how the important rocketry variables of interest evolve over time during the launch, say the optimization group in your company wants to know the instantaneous mass at any given instant during the launch. Okay, what is instantaneous mass? Fire up Photoshop again, and okay. So when the rocket is being launched, a tremendous mass is actually being lost in the form of burnt fuel, and the mass of the total rocket system is actually changing every second. Okay, so the instantaneous mass is given by this equation, 1875 minus 1.997 multiplied by the time instant. By the way, this equation will vary depending upon the rocket configuration. So this equation is not for this particular rocket, but for a fictitious rocket. All right. Okay. So using Newton's classical mechanics, you come up with the formula for the instantaneous mass of the rocket, which is this equation here, and this is just crying out for a Matlab function. Okay, so say your rocket modeling group or the trajectory optimization group in your company wants to just input the time instant. Okay, and the function that you write, it needs to output the mass of the rocket for that instant. Okay, so let's go back to Matlab. I just want to show you the function calculate instantaneous mass. Okay, so look at the function syntax. The name of the function is calculate instantaneous mass, inst mass. It has one input argument and it has one output. Note, input is actually contained between normal brackets and the output is actually contained between square brackets. So it takes one input and uses this equation, and this is the output. So it's pretty simple to understand. So the Matlab function syntax, it's easy to understand. All right, how do we use this function in a script? So let's say I just want to say close all and clear variables, and I'm going to put a breakpoint here. I'm going to run the script. Continue. Okay, we got the figure. Not yet. Okay, there you go. Continue. All right, this is the figure that we talked about earlier, and this is where in this section I'm actually calling the function. Your optimization group is actually telling you find the instantaneous mass of the rocket at time instant equals 100, and we want to see whether we have data for the exact time instant 100. If you just go to the time vector, so we don't have data for exactly 100 seconds, but somewhere close, 101.76 seconds. So what we will do is we will set time instant equals 100, and we want to find the vector index that is closest, greater than or equal to time instant, and we just want to find the first element. Again, this is all known stuff. So if we execute this line, step and step, the vector index is actually 35. Right, 35. So we found this element. Okay, and the vector index is 35, and the time instant is 101.7640, which is pretty close, which is the closest as we can get to 100 seconds. All right, then we find that with the element in the time vector which corresponds to this vector index, which is 35, and we said that it is 101.76 seconds. So that's the input argument. And if you want to step into the function, you can say step in. You go into the function, and this is a pretty simple equation. It takes the input argument, calculates the instantaneous mass, and actually comes back. All right, and this line, this just prints the instantaneous mass and the time instance to the command window. All right, so now your group, optimization group, is actually calling for another function. They're telling you, I want to give you the time instant, and you tell me, you calculate the drag, the instantaneous drag for the rocket at the time instant. And you write another function, calculate instantaneous drag, that actually takes 3 input arguments and returns 1 output argument. Okay, so it takes the rocket height, the rocket speed, and the earth radius. And how we call that one is, again, same as before. Let's say this time we want to find the instantaneous drag at 120 seconds. We find the vector index, and we find the height. Okay, so we find the element from the height vector that actually corresponds to this vector index. Again, we find the element in the airspeed vector that corresponds to this vector index, and the earth radius. And you will understand why we need the earth radius in a second. So we step into the function. Okay. Now, the height of the rocket in the equation that you developed is the height from the center of the Earth. So, in order to find the atmospheric height, you need to subtract the earth radius from this height variable, and this is height above ground. Step, and this is the drag equation we talked about. We are implementing this equation in Matlab. This is the exponential part, and this is actually the quadratic part. And step. All right. And this is again printing to the command window. So for the time instance, we we don't have data for exactly 120 seconds, but we found the closest match, which is 120.64 seconds. The drag at this instant is this many newtons, because drag is a force which is being measured in the SI system in newtons. Now I want to talk about Matlab functions that can actually accept multiple inputs and give out multiple outputs. And let's go take a look at this new function called calculate mass and drag. Again, the optimization group actually tells you, hey, I will give you the data file for the rocket launch, and I'll give you the time instant of interest. You calculate the instantaneous mass of the rocket and the instantaneous drag of the rocket at that time instant. Now, you can call this Matlab function from the command line like so. You can call it from a script too, but I just want to show you how we can call a function from the command line. Okay, so the first argument is the data file, and we give the name of the data file within quotes, rocket launch data.math, and the time instant that we're interested is 110 seconds. And the function, note that it has two output arguments: instantaneous mass of the rocket, instantaneous drag of the rocket. Okay, and let me put a breakpoint here, and if I just execute it from the command line, we will stop here. We are loading the data file. This is known stuff, and finding the vector index, this is also known stuff. We talked about it, right? We find the time instance, and we find the height, rocket height, and rocket height above the ground, and the rocket speed. And once we know these variables at the time instant, we can calculate the instantaneous mass of the rocket, and we can calculate the instantaneous drag of the rocket using this equation. And notice, once the function is done executing, the output arguments are actually being printed to the command window. Mass of the rocket at that time instant is 1.6502 10 to the power 3 kilograms, and the drag is 3.0961 10 to the power 5 newtons. All right. Okay, so that's it for this video. I hope this was useful, and I will see you in the next video. Thank you very much.